welcome back. In the last class we had started looking at the specific equilibrium, which is the vapor liquid equilibrium. We are going to derive useful relationships at vapor liquid equilibrium conditions. We had already looked at a pure substance in vapor liquid equilibrium. We said that the conditions of equilibrium need to be valid, therefore Tv equals Tl equals say T sat and Pv equals Pl equals say P sat. This we are going to take as a given, and mu v equals mu L is what we said. We looked at this particular equation further, and using the expansions or the definitions of the chemical potential in terms of fugacity that we had developed in, or that we had given in module 3, we wrote mu naught plus RT ln Fv for mu v equals mu naught plus RT ln Fl for mu L, and we could see that the fugacities are equal of water in or of the pure substance in the vapor phases and the liquid phases. From this and just the definition of the fugacity coefficient, we could write a relationship between the fugacity coefficient and pressure. Phi v Pv equals F sat, or in other words phi sat, phi v is nothing but the value at the saturated value under the conditions of vapor liquid equilibrium. Phi sat P sat equals F sat. This was equation 528, and what was left as an assignment for you was to develop similar expressions for a multi component system. This is for a pure component system, and you are asked to develop equations for a multi component system. Hopefully you could do that, and let us see how they look at now. From mu v equals or mu I v equals mu I L for a multi component system, that is the chemical potential of the species I in the vapor phase must equal the chemical potential of the species I in the liquid phase, and if we expand it as mu naught plus RT ln F I v hat, that is how we write the chemical potential is related to fugacity in the case of a multi component system. Therefore F I v hat equals F I L hat is what follows from mu I v equals mu I L. We will call this equation 529, and using equations 47 and 48 from module 4, you will realize what those expressions are. Mu I equals mu I hash plus RT ln phi I y I, this is what we got in 47 and 48, that is mu I naught plus RT ln phi I p y I 47, and mu I equals mu I hash plus RT ln gamma I xi. This is for the liquid phase and this is for the vapor phase, and for the liquid phase this further equals mu I naught plus RT ln gamma I fi xi. This is equation 4.8, or this was equation 4.8. We said that this is the condition, and if we even if we do not look at it, if we just go ahead and equate these two, we get mu I naught will cancel out, RT will cancel out, therefore phi I p y I equals gamma I fi xi. This equation 530 is the condition for equilibrium of this is for a species I, you can write this for a species I at vapor liquid equilibrium conditions. So hopefully you would have gotten at this, if not, this is the kind of expression that we were looking for. Now let me give you some sort of a real world example and give you some time to work it out, and the answer is very simple, but it requires some bit of thinking, so I am going to give you enough time for that. The example 5.3 reads as: the volumetric oxygen transfer coefficient KLa of a bioreactor volumetric oxygen transfer coefficient, is denoted as KLa. KLa of a bioreactor is typically measured without cells being present in the broth. Air is bubbled through the broth and the oxygen gets transferred from the gas bubbles to the liquid broth. At the end of the estimation, the oxygen concentration no longer changes in the broth or the bioreactor headspace. Under such conditions, based on what has been learnt in the module, what can you say about the relevant thermodynamic property of oxygen? I have worded it this way for a specific reason. I would like you to go through what we have covered in this module and come up with a solution. The solution is very simple, it is a straightforward thing, it is a very simple thing, but it will require some bit of thought, especially when you are doing it for the first time, and I will just show you the solution when we come back. Go ahead please. Okay. Hopefully, you got that simple solution. If not, the thinking is something like this. Under the conditions given in the problem, equilibrium exists between the phases. Note that there was oxygen that was transferring from the gas bubbles to the liquid phase, and then after a while there is no consumption of oxygen anyway, and therefore the concentration of oxygen in the broth is not going to change, and therefore the consequently the head space oxygen concentration is also going to remain the same. Therefore, there has been a condition of equilibrium reached between the liquid and the vapor phases, or oxygen in the broth and oxygen in the vapor phase has reached a certain state of equilibrium. So, these are the phases that are of interest here, the vapor in the head space and the liquid in the broth. We are interested in the thermodynamic property under such conditions, and of course, the temperature and pressures you need to appropriately look at, but we are not really going to focus on that. From one of the conditions of equilibrium, equation 526, we can write the relationship for the chemical potential of oxygen. This is what we are looking for, and this is what we are going to write. The relationship for the chemical potential of oxygen is going to be that the chemical potential of oxygen in the vapor phase must equal the chemical potential of oxygen in the liquid phase. This is the condition that will be valid under the situation given in the problem, and from this you can come up with something useful, but that is not in the scope of this particular problem. Okay. So, you would have had a chance to look at whatever we have developed in the context of a real situation. Let us move forward. What we are going to see next is the estimation of the fugacity coefficient from the pressure, specific volume, temperature data at equilibrium. Note that we have already seen a method of estimating the fugacity coefficient at the end of a previous module, and this is going to be another method from the PVT data at equilibrium. So, we are going to use the condition of equilibrium to devise a method to estimate the fugacity coefficient. For a pure component, we have already seen this equation in module 3, d mu equals V dP under certain conditions. This was 353, and d mu equals RT d ln f. This was equation 354, f being fugacity. So, since these are equal, if we equate these two, we would get RT d ln f equals V dP. Let us call this equation 531. If we integrate this expression between saturated value and a particular pressure, let us say P1, we would get, this is RT d ln f. We are going to integrate between a saturated pressure and a certain P1. Therefore, we will have to integrate the right hand side also. First, let us see the left hand side, d ln f, therefore, ln of f by f sat, ln f minus ln f sat, which is going to be ln of f by f sat, that equals 1 by RT integral from P sat to P1 V dP. Let us call this equation 532. If you recall, this is the molar liquid volume. The molar liquid volume is typically a weak function of pressure. At the temperatures well below the critical point, we really do not have to worry about its variation with pressure. Therefore, for all practical purposes of interest, this V can be taken to be a constant in this particular integral. It is a very good approximation. And what we are going to do now is to avoid the difficulty between, or the confusion between, the vapor and the liquid phase volumes. We are going to use another subscript L to represent, or to make it clear that it is the molar liquid volume, and so therefore we are going to call it as VL. This is actually a superscript L, and we are going to call it as VL. Therefore, we will get ln of F by F sat equals, this is 1 by RT, V also is a common, or VL is a constant that has come out, therefore VL by RT, and integral of P sat to P1 dP is nothing but P, or P1 minus P sat. We are just going to drop this 1 here, therefore P minus P sat, or F by F sat equals exponential of VL into P minus P sat by RT. Earlier there was a log here, therefore F by F sat becomes exponential of the right hand side. Let us call this equation 533, and while we are doing all this, our main aim is to get at an estimate of the Fugacity coefficient. Let us see how to go about doing that. This right hand side of this expression is actually called as the pointing factor. F by F sat equals this exponential of VL P minus P sat by RT, this is the pointing factor. Further, using equation 528 become clear right now, phi sat P sat was F sat, and this is again pure substance, so phi sat P sat equals F sat is valid here. This was 528. We can write 533 as F equals phi sat P sat exponential VL P minus P sat by RT. Now F by F sat was exponential VL P minus P sat by RT, therefore F equals F sat exponential VL P minus P sat by RT. You have just replaced F sat by phi sat P sat. Let us call this equation 534. Now phi is nothing but, the Fugacity coefficient is nothing but F by P. Therefore, the above equation can be used to find the Fugacity coefficient of a pure component, that we have somehow arrived at in, but let us clarify that a little further. That was for a pure system. We need that for now, we need to look at a multi component system, that is what I meant by clarifying further. We need to do it for a multi component system. For a multi component system, this equation 530 is valid, which is phi I P y I equals gamma I F I x I. This is what we derived, in fact you had derived for a multi component system, the condition for equilibrium being this, phi I P y I equals gamma I F I x I, equation 530. Note that the F, which is Fugacity of a pure component, equals F I, which is the Fugacity of the pure component I at the same temperature and pressure as that of the solution, that is the Fugacity when phi y I equals 1, when the mole fraction equals 1. Therefore, using equation 534 to substitute for F I in 530, we get phi I P y I, that is the left hand side, equals gamma I, same as gamma I here, x I same as x I here. Instead of F I, we are going to write phi I sat P I sat exponential of V I L into P minus P I sat divided by R T. We just substituted F I with the one that includes the pointing factor here, which can further be written as phi I into P y I, which is the left hand side, equals gamma I P I sat x I. Now this, if you are able to see this, have let me show you what phi is, then it will become easier. This is what we have here. We have written this expression as, this is a okay, let us call this phi. Okay, this is not phi, let us call this phi. Phi I into p y I equals gamma I p I sat x I, which means the remaining terms have all been combined into a phi I, which is what will be shown here, where phi I equals phi I divided by phi I sat exponential of minus V I L p minus p I sat by R T. Let us call this equation 536. And what usually happens is that the exponential term is close to unity at pressures of relevance to most biological systems, which is typically atmospheric pressures and so on and so forth. Therefore, this term can just be replaced with a 1 for most biological systems, and the following approximation works very well, which is phi I equals phi I by phi I sat, equation 537. The value of phi I can be estimated from the second virial coefficients. Remember that B11, B22 and so on and so forth. We can use that to estimate phi I. I am just going to state it here, I am not going to derive it in here. The derivation requires probably some understanding of statistical mechanics. So, since that is outside the scope of this course, I am just going to mention this here. Phi I equals this complicated expression, let me just read it out to you, equals exponential of BII p minus pi sat plus half and twice summed over j and k yj yk 2 delta ji minus delta jk. I will tell you what deltas are, delta 2 delta ji minus delta jk divided by RT. This is equation 538, where delta Ik equals 2 Bik minus Bii minus Bkk, and delta Ij equals 2 Bij minus Bii minus Bjj, and delta Ii equals 0, delta Kk equals 0, and delta Ki equals delta Ik. Therefore, there is a way of estimating this phi I from the second virial coefficients, and going back you can get the other quantity that we are looking for. And what we did in this particular section is to look at a way or a method of estimating the fugacity coefficient from the conditions of vapor liquid equilibrium. Since the other things are slightly different, let us start them in the next class. We will stop here for this class. See you then.